This video is about what are like terms. So very, very important concept in algebra, and we've just started this topic, so I'm going to get you to do a lot of the thinking. In this table, I've given you two columns, and the first column is a whole bunch of terms or examples of terms that are like terms. So for example, here we've got 5m and 11m. Those are both like terms, and I've given you 7 different examples. So we've got another set here, another set here. And you're going to look at each of those examples and think about what makes them like terms. Now, I know you don't know what like terms are at this point, but you have enough examples to try and draw some or make some guesses, some conjectures about what you think makes these terms like terms. And there's about 2 big ideas for what makes a pair of terms or a group of terms like terms. And this column gives you a whole bunch of examples of pairs of terms that are not like terms. So what I want you to do is pause the video at this point in time and spend a good few minutes thinking about what makes 2 or more terms like terms, so using that first column, and then with your thoughts check that that would work for the second column. So for your rules about what like terms are, does that agree with why the second column contains pairs of terms that are not like terms? So you can actually test out your rules. So please pause the video now, and when you've come up with your ideas or you've scribbled them on paper, you can press play and see if you are correct. So now's the time to pause. All right, let's see if you were correct. There are 2 things I'm hoping you noticed in the slide before, and that's that with all the pairs of like terms, all of the pairs had the same P word. We've got pronumeral, okay, that same letter. So all the pairs of like terms had to have the same letter. If they didn't have the same letter, then they would not be like terms, okay? And sometimes you have more than one pronumeral, so you might have like AB or XYZ. So you needed to have the same combination of pronumerals if you have multiple letters. So you need the same pronumeral or maybe pronumerals. And the other thing you needed is to have the same power. Power, indice, exponent, whatever you want to call it. And let me expand on that in point number 2. So each pronumeral, so if you look at this example here, we've got an F squared and a G. So my pronumerals are F and G. And here we've got F squared again and a G. And that's what makes them like terms. I've got the same pronumeral, but each pronumeral has to be raised to the same power. So if we look at the next example that looks awfully similar, we have an F squared here, but in the second second term, only the G is being squared. So instead of having an F squared in both terms, in the second term, it's only an F. And that's a problem because you need each pronumeral must be raised to the same power. So if you have, say, an A that's been cubed, then in the other term, it also must be cubed. If you have a C squared in one term, then it must be C squared in the other term. It's not enough just to have the same letters and powers moving around. Each pronumeral must be raised to that same power in every single term. And that's why these are not like terms, but these ones are. The order of the variables doesn't matter. So that also showed up in the last slide. So for example, if we have PQR, you can also have QRP because we've got the same pronumerals. So we've got a P and a P, a Q and a Q, and then an R and an R. So because we know that in algebra, when you've got variables or pronumerals joined together and there's no sign joining them, then there's a multiplication sign. And so using our knowledge of the commutative law, we know that PQR is exactly the same as QRP because with multiplication, the order in which you multiply doesn't matter. So if we look at this second example and why these are not like terms, well, we've got a P, but over here, no P. So we can have a QR. So we've got the QR in both of them, which is good. But as soon as you don't have the exact same combination of pronumerals, they are no longer like terms. So that's also very important. So we're looking for the same pronumerals. We're looking for the same power, but each pronumeral must be raised to that to the same power in each term. And also the order of the variables or the pronumerals, the order does not matter. So time for a quiz. I'm not sure what that's doing over there. We'll just ignore it for now. The quiz is, are these like terms or not? So this is your turn now to pause the video and to have a think about each of these examples, decide if they're like terms, and this will check your understanding. Do each set of terms have the same pronumerals? Is it the exact same combination of pronumerals? If there's more than one pronumeral, is each pronumeral raised to the same power in each term? Does it matter if the pronumerals are in a different order? So those are all the concepts for you to think about. Pause the video, decide on which sets of pronumerals, and then unpause it when you're ready to hear the answers from me. All right, first question. We've got P. The coefficient, which I haven't mentioned so far, the coefficient doesn't matter. Doesn't matter what it is. The coefficient can be anything, fraction, decimal, negative, positive. It's the pronumerals I'm interested in for like terms. So we've got a P and a P. They're exactly the same. They're like terms. For number 2, I've got an N and an N squared. That's a problem because the N isn't being squared in both terms, not like terms. Here I've got an H squared, so I'm going to look over to the next term and find that that is not an H squared straight away, not like terms. Here I've got a B squared. Check the other term. Yes, I've got a B squared. Then I have an A. Check the other term. I have an A, like terms. M and M, both raised to the power of 1, like terms. Y raised to the power of 1, another Y over here to the power of 1, like terms. It does not matter what your coefficients are, so it doesn't matter whether they're negative, positive. If I can't see anything, I know there's a 1, but that also doesn't affect whether they are like terms. U in this example, G and G all have powers of 1, like terms. Let's do our last one. R squared, R cubed. That's a problem. They need to be the same power. So here I can see we've got a U cubed and a U squared, not like terms. So obviously, definitely not like terms. I hope this video has helped you with your understanding of the difference between whether a set of terms are like terms or not.